Welcome to Module 4 of the AIA Structural Exam Preparation course. I'm Dilip Khatri, and today we're going to do some example problems dealing with shear and moment diagrams. In the previous module, I showed you how to do shear diagrams and moment diagrams separately, and I thought it would be useful for us to do some actual examples. So let's take a look at our first example, and I'll sketch it out for you here. It's a fairly straightforward beam. It's a simply supported beam, 10 feet long, with two loads, 1,000 pounds and 2,000 pounds. At 2 feet, 4 feet, and 4 feet. So the first thing you do when you do a shear moment diagram is you want to draw a series of lines down the diagram to indicate the critical points in the shear diagram and the moment diagram. And what are the critical points? Well, obviously the end points where you have your reactions, and we'll put some labels on here in a moment. We'll call this A and B, reaction RA, reaction RB. And then we draw a couple of dashed lines where the loads are occurring, because we know that there's going to be some activity on the diagrams at those points, just as a kind of a standard procedure. And the first thing we got to do is we got to calculate the reactions. There are several ways to do that. In this case, I'm going to show you a couple of different ways. We'll first do the sum of the moments about the B, point B, using clockwise positive. And so if we do that, we have RA times 10 feet minus 1,000. RA times 10 feet minus RA minus 1,000, which is this force, times 8, minus 2,000 times 4 must equal 0, just using basic statics. And so that becomes 10 RA minus 8,000 minus 8,000 equals 0, or 10 RA equals 16,000. I'm going to be numbering all of my sheets on these notes so that we'll have them available for you. So that's sheet number 1. So following up from the first sheet, where we have 10 RA, so therefore RA equals 16,000 divided by 10, which is 1,600 pounds. And then to get the other force, the RB, we can use sum of the forces in the y direction equal to 0. And so that's RA plus RB. The vertical forces going up must equal the forces going down. So RA plus RB must equal 3,000. Which tells us, since we already know RA, that RB is 3,000 minus 1,600, which is 1,400 pounds. So now we have the reactions. Now there is also a shortcut way. I'll just take a moment and show you a shortcut, okay, on how to do that. And that comes from a basic equation that we use in structural analysis for load on a simply supported beam, and it might be of some use to you when you're on the test, and I'll quickly show that to you. Here we have a simply supported beam with loads A and B, and I'm going to put a load somewhere along the length. We'll call it P. And the spacing of that load, let me identify some of the dimensions. Our dimension here is L, and our spacing is A and B. I'm going to show you a little shortcut. I'm going to take a little divergence from solving this problem just to show you a little shortcut that will be of some use to you, I'm sure. So we have a simple beam here. It has a spacing AB, A to the left reaction, B to the right reaction with a span of L. Right away, the A reaction and the B reaction is the load P times the distance to the right support divided by L, and vice versa for the right reaction. You can always remember that. It's a good little rule of thumb to remember. And you can test it out. For example, if B were equal to L, then A would equal P. If B were to equal A, or excuse me, let's do that again. If A were to equal L, then capital B would equal P. And all it says is that as the load moves closer to this side, this reaction takes a higher proportion of the load. So whenever the load is closer to the reaction point, more of that force goes into that reaction and vice versa. So if we were to use this approach, we could solve this problem for reactions much quicker. We'll take a second and show you how we could do that. So if we go back and try to use the shortcut approach, here's our reaction A, here's our reaction B. So let's do this again, and this will be page 3. Our reaction A would equal the proportional contribution of the 1,000 pound plus the 2,000 pounds. So it's 1,000 pounds times the distance to the right support, which is 8 over 10 plus 2,000 times the distance to the right support, which is 4 over 10. So this becomes 800 plus 4/10 of 2,000, and that cancels into here, becomes 200 times 4, and that's also 800, and that becomes 1,600 pounds. And as you can see, it's the same answer. The two are they're the same answer. They have to be the same answer. If they're not the same answer, you did something wrong. So that's just a little shortcut. Let's go back to solving the problem now. So we have our reaction here on the left, 1,600. We have our reaction here on the right, 1,400, and let's draw the shear diagram. So 1,600 on the left means that we start off with an upward immediate positive start on the shear diagram, and that continues until you reach the first load point, in which case it drops down by 1,000. So 1,600 minus 1,000 puts us at 600. So this drops down, and that remains constant until you reach the 2,000, which then it drops down 2,000, which puts us at minus 1,400. So this drops down, and then that stays constant until we reach the reaction point on the right. There's our shear diagram. So remember that your shear diagram, which started at 0, went up, went through the fluctuations, always comes back to 0. Same thing is true with the moment diagram. The moment diagram is going to start at 0, and it has to come back to 0. We have to calculate the areas under the shear diagram in order to give us the values of the moment diagram. So the area of the first portion of the shear diagram, and I'll just put numbers on here for now because it's a little hard to write in here. I'll call this A1, A2, and A3, and let's do those calculations. Normally you could write them right in here, but because I'm doing this on the screen and the pen is a little thick, I don't want to complicate that. So areas under the shear diagram. And so A1 is going to be the area of this rectangle, which is 1,600 times 2. So it's 1,600 pounds times 2 feet, or 3,200 foot-pounds. That's my first area. Area A2 is 600 times 4 feet. 600 times the length, 4 feet. This is 600 here, is the height, and 4 feet is the length. 2,400 foot-pounds. A3 is going to be 1,400 times 4 feet. So 1,400 times 4, 5,600. Now notice that A1 and A2 are both positive. A3 is negative. This is negative. These two are positive. And just a quick check, if we were to add all of these, they better come up to be 0. If they're not 0, we know we have a problem. So when we add these up, we have plus 5,600 minus 5,600 equals 0. So that's good. Okay? That tells us that everything is balancing. Now we can draw the diagram. So we go back to the original diagram, and the first portion of the shear diagram is going to climb linearly up to plus 3,200. The next portion of the shear diagram is going to climb linearly to plus 5,600, and these are all in foot-pounds, and then it's going to go negative down to 0. And that's your shear and your moment diagram. Let's try another example. Let's do a cantilevered beam. So let me label this example 2. This will be sheet 4. And we'll make this a cantilevered beam. With a uniform load. We'll label this as A, point B. We'll make the distance 12 feet, and the load is 1,000 pounds per foot. So shear and moment diagram. Again, same thing you do. You're going to draw a series of lines to mark where the loads. I'm not drawing anything in the middle here because we only have a uniform load. So here's our shear diagram. Here's our moment diagram. Let's first calculate the end reaction. End reaction is fairly straightforward on this problem. Reaction RA is going to equal the sum total of this uniform load, which is 1,000 pounds per foot, times the length, which is 12 feet. So that's 12,000 pounds. And that's our reaction. So we already know that our reaction is 12,000 pounds. The moment at A is going to be the moment of this uniform load, which can be symbolized by a concentrated load. In order to calculate the moment, we can simplify the uniform load by a concentrated load, W, equal to 12,000 pounds. And then the moment about point A is that force W times L over 2. So it's 12,000 pounds simulated at the center of the uniform load times half the span, which is 12 feet divided by 2, so it's 6 feet. And so this MA becomes 12,000 pounds times 6 feet, or 72,000 foot-pounds. So we have the end moment, 72,000 foot-pounds. We have the end reaction of 12,000 foot-pounds. So the shear diagram is going to start at plus 12,000 and is going to end up at 0. Let's talk about the shape of the shear diagram, because the shear diagram is related to the loading in the following manner. And it's just a quick explanation. So the shear diagram, the Q is my loading, is the derivative of the shear diagram divided by, the derivative of the shear diagram versus the length. And the shear diagram is the derivative of the moment per unit length. Which means that if my loading is negative, then my slope of the shear diagram is negative. And similarly here, if my shear diagram slope is negative, value is negative, then the slope of my moment diagram will be negative. That's what this is telling us. So all that means is that if my load is a linear load, in this case it's a constant load, then my shear diagram is going to have a straight direct slope, because this value up here is a constant. And I can show you what that means mathematically. And the slope of the moment diagram, because the moment is the integral, taking this equation, means that the shear diagram is the integral of my load diagram, and working with this equation over here, the moment diagram is the integral of the shear diagram, which means that the shear is equal to the area under the load diagram. And here the moment is the area under shear diagram, just using basic calculus. But I don't want to make things complicated for you. So when you look at this load diagram and it's a constant, you automatically know that this is going to be a linear diagram, because from basic calculus, if I integrate a function, we'll do this for you in a moment, page 6. Using that basic calculus, if my Q is a constant, and we'll just say for right now it's W, then my shear diagram is the integral of W dx, which will be Wx. If it's negative, then it becomes minus Wx. This is a linear curve. It's a straight line curve with a y-intercept, we'll call it plus b. If I integrate that one more time to get the moment diagram, then the moment diagram, which is the integral of the shear diagram, and that's the integral of minus Wx plus b dx, becomes minus Wx squared over 2 plus bx plus another constant, we'll call it c. And this is a quadratic equation, or what we call a second degree curve. This is a first degree curve. So all that means is that this is a linear, and second degree curve means that it's a parabola. So going back to sheet number 4, how does it look? Well, that's a linear curve. It's a straight line. And the parabola, before we draw the parabola, we have to get the values straight. What's the curvature of the moment diagram? Well, the elastic curve is going like this. This is my deflection. And what did we learn about an elastic curve shaped like that in the previous lesson? Refresh your memory. Remember, this will be sheet number 7. Remember from our previous lecture, positive moment, negative moment. This refers to the elastic curve. If a beam is bending with tension on the bottom and compression on the top, positive moment. If a beam is bending with tension on the top, compression on the bottom, negative moment. Going back to this diagram, what do we have? We have tension on the top, compression on the bottom, and it's a negative moment. Everybody see that? You have negative moment, tension on the top, compression on the bottom. So negative moment means that our 72,000 is a minus 72,000. Now the curvature is going to go from minus 72,000, and you can double check the math. We'll do it again right now. The area under the shear diagram is 1/2 12,000 times 12 feet. That's 144,000 divided by 2, which is 72,000. That matches with this. This is a positive area. So we're starting with a negative moment and we're going to go positive. Now what's the shape of the moment diagram? Well, going back to the equation that we learned, that the shape of the moment diagram, the slope of the moment diagram is the value of the shear diagram. Therefore, the slope of the moment diagram, here the slope of the moment diagram is going to be plus 12,000 because that's the value of my shear diagram. So I'm going to have a very high slope here. And here, since my shear is 0, my slope of my moment diagram will be 0 here. Here, my slope of my moment diagram is plus 12,000. Here it's 0, so the curve looks like this. Shear diagram, moment diagram. Let's do another example. This is a slightly more complicated problem. This will be a beam, and let's draw it out. So this will be page 8, and let's draw our beam. This is a simply supported beam with multiple loads on here. So we have a support point here, a support point here. We have a uniform load. We have a cantilevered load, a uniform load, cantilevered load, this uniform load, 2 kilonewton per meter, concentrated load. We'll label these points A, B, C, D, and E. And as we did on all the previous problems, we'll first label, put our lines down. And the first step is for us to calculate the reactions. So we have our shear diagram and our moment diagram. First step, calculate reactions. So let's do that. Sheet number 9. And the way we can do that is we'll sum moments about point D to calculate reaction B. Sum moments about point D equal to 0, clockwise positive. So that will be minus 5 kilonewtons times this distance, let's put our distances down. Two meters, 2 meters, 4 meters, and 2 meters. We have -5 times 2 plus 2 plus 4. So that's 8. We have -15 times 4. And I'll do this 2 kilonewtons. Let's first do the reaction B. Reaction B times 6. And then the 2 kilonewtons, which is a uniform load, times its length, which is 2 plus 4 plus 2, that's 8 meters. And then the distance, which is going to be at the center. We can simulate this as being at the center, so that's 2 times 8, that's 16 kilonewtons, times this distance to the reaction. And since it's at the center and the total length is 8 meters, this will be at 4 meters, so this has to be 2. 2 meters to the reaction point, because this is at the center of gravity of that uniform load. So it's 2 times the 8 meters times the moment arm, which is 2 meters, equals 0. So you have -40, -60, plus 6b, minus 2 times 8, 16 times 2, minus 32, equals 0. Or 6b equals 132, which is 132 divided by 6. Therefore, B is equal to 22 kilonewtons. That's our first reaction. The second reaction, which is D, we can do by sum of the forces. So we can do that, sum of the forces in the y direction. And so that would be B plus D should equal all the forces going downward. So we have -5 minus 15 minus 2 times 8. And B we have determined as 22. So we have the sum total of this is 20 minus 16 is minus 36. And excuse me, let me make one correction here because I already put this on the right-hand side, so I can actually go ahead and change the sign. It was negative if it was on the left-hand side. So minor correction there. So B is 22, so D is going to be 36 minus 22, which is 14. So that reaction is going up. So now we have our reactions. We have 22 and we have 14. We're ready to draw the shear and moment diagram. So this is a negative load, so it'll be -5. It's going to remain constant until we reach this point where it's going to go up by plus 22. So it's -5 plus 22, which gets us to plus 17. And then it goes down by the slope of the load diagram. So this will be a trapezoidal shape here, and it's 2 times 2, which is 4. And how did I get that? Let me draw that. Let me do that calculation for you on the shear diagram. So at point C, I'm going to try to explain that. At point C, what do we have? We have the -5, we have the reaction 22, and we have this load. And so to calculate that shear, we know that we started off here at -5, and I'm just going to draw a portion of the shear diagram to explain. We started here at -5, we went up to plus 17, and now we're going down. And the question is, what's that value? Well, that's going to be 17 minus this value, w, which is 2, times the distance x. In this case, the distance x is 2 meters. So it's 17 minus 2 times 2, which is 4. This becomes 13 kilonewtons. Okay, that gives me this point right here. So going back to the shear diagram, this is going to look like this. And we're going to be at plus 13, and then it goes down another 15. It drops 15 down to minus 2. And the reason it drops 15 is because of the 15 kilonewton load, and then it continues dropping until you reach this reaction point here. How much does it drop? Well, it's 4 meters times 2. So it's 4 times 2, which is 8, minus 10, minus 2. Let me do that for you. So continuing on, here we drop down to minus 2, and then we keep on going, and we end up at this point over here, where this is at point D. And this point right here is going to be minus 2 times 4, which is 8, so that becomes minus 10. So at this point, we're at minus 10. And then we're going to jump up the 14 kilonewtons from the reaction. So now we're going to be at plus 4. So this is going to come up here to plus 4. And then it's going to continue dropping again, and it's going to end up at 0 because we have 2 times 2. Again, 2 kilonewtons per meter times the 2 meters, we end up at 0. There's your shear diagram. Now we calculate the areas, and I'm going to label these 1, 2, 3, and 4, so that we can calculate the areas inside the shear diagram so that we can draw the moment diagram. Let's do that. Area of shear diagram. Area A1. A1 is pretty simple. It's a rectangle, and so that is 5 kilonewtons times 2 meters, or 10 kilonewton meters, and it's a negative area. So here we have an area which is 10. I put in parentheses to show that it's a negative area. Then we have a trapezoid. Trapezoid can be calculated in 2 different ways. You could break it up into a triangle, or you could do 1/2 sum of the bases times the height, the average base times the height, either way. It turns out to be the same thing. So area A2 is equal to, let's split it up into 2 pieces. So we have 13 kilonewtons times the length, which is 2 meters, plus 1/2 the height, which is 13 from 17, which is 4, times the base, which is 2 meters. So that becomes 26 plus, these two cancel, plus 4 equal to 30 kilonewton meters. That's A2, and that's a positive area. This is a negative area. This is a positive area. A3, same thing. We have a trapezoid. We're going to break it up into 2 pieces. We have the rectangle, we have the triangle. So the first piece is 2 times the length, which is 4, plus 1/2 the height. The height is 10 minus the 2, so the height is 8 times the length, which is 4, and that becomes 8 plus 2 goes into this 4, 16. That becomes 24, and that's a negative. Why is it negative? Because we are in negative shear. So that's my A3. A4 is just a simple triangle. It's 1/2 the height, which is 4, times the length, which is 2. And so that becomes 4 kilonewton meters. And that is a negative area. Let's see how this plays out now. Let's plot it. Our moment diagram starts off at 0, is going to go down to minus 10 linearly. Why? Because this is a constant. This is a linear curve, so this is going to be a parabola. The shear is negative. So this area we got, that was A2. A2 was 30. So what that tells us is that our peak, which is up here, is going to be plus, it's going to be minus 10 plus 30, which will be plus 20. Let me write that out for you. Page 12, moment diagram values. M1 is minus 10. I'll call this point number, or actually let's use letters. Let's call that B. MB is minus 10. The moment at C is minus 10 plus the area of the shear diagram, which was 30. And so that becomes plus 20. And that is a point of maximum because the shear there crosses the 0 line, which implies that the slope of my moment diagram is 0. So the curve is going to look like this. And then M3, or rather MD I should say, is going to be plus 20 minus the area, what we labeled as area 3. Going back to sheet number 11, area 3 was minus 24. So you have plus 20 minus 24, you end up with minus 4. So what's the slope going to look like? Well, this is going to be minus 4. And it's going to be negative because my shear diagram is negative, so the curve is going to look like this. And all of a sudden, the shear goes positive, so my slope is going to be positive, and here it ends up being 0, and this is 4, we end up at 0. There you go. Shear and moment diagram. Shear diagram, moment diagram. Looks like you had enough. Take a break. We'll come back for more. Thank you.